Hi everyone. We're going to go over how to name ionic compounds. The key thing with ionic compounds is that the total charge of an ionic compound has to add up to zero, right? So we have to choose a ratio of the ions so that no matter how many there are, that for that ratio, the charge comes up to be zero. So for example, if you have the compound calcium chloride. Calcium, as we're going to see how to figure out in just a moment, always has a 2 plus charge when it's in an ionic compound. Chlorine, when it's in an ionic compound, always has a charge of -1. So what we have to do is choose a ratio so that the total charge comes up to be zero. And what that means is simply we need to have two of the negative ones for every one of the 2 plus charges. So if you could see this at the atomic level, what that means is that every calcium has to have two negatively charged Cl minuses around it, all right? This would form a lattice structure, as we've seen in previously, because that's the structure that ionic compounds take. And this would go on pretty much forever uh, in all directions in 3 dimensions. And we're not going to worry too much about exactly what it looks like, but we know that there's some sort of repeating lattice to that structure because it's ionic. So, and within that, no matter what grouping you took of this, you would always find, so if you just pulled out these 4, you would always find that there's 2 chlorides for every 1 calcium. So we're going to cleanly rewrite that formula as CaCl2 without listing any of the charges. And that is going to be our rule. The total charge has to always be 0. Let's say you had another compound that contained aluminum with chloride. Aluminum's always 3 plus when it's found in ionic compounds. The chloride would be -1 again, and that means that there need to be 3 of the aluminum chlorides in order for the total charge to come up to be 0. All right? There's some other more fun ones where you have 3s and 2s. Let's say you had aluminum with sulfide. Sulfide is always 2 minus in an ionic compound. So the only way to do this, and you can play around with the pictures, drawing pictures like the one I did over here for calcium chloride, the only way to get this to come out to be 0 is if there's 2 of the 3 plus ions and 3 of each of the 2 minuses, all right? So this is going to be that'll be a total, you can think about this as a total of 6 plus for 2 aluminums and a total of 6 minus for the 3 sulfides. So that's going to be Al2S3 for aluminum sulfide. All right. And again, the only thing we're doing here is trying to make the total charge of the compound come up to 0. Now, how do we know what the charges are going to be? So some of these we can get off the periodic table. So if we think about the periodic table, and this is my crummy imagination of the periodic table, if an ion, a cation, is in this first column of the periodic table, it's going to have a +1 charge. Now, I keep saying when it's in an ionic compound because people forget that if it's an element, it's 0. So if you have sodium, it's 0 as an element. But when it's found in an ionic compound, it's +1. Same for lithium. As an element, it's 0. In an ionic compound, it's +1. Anything in this next column over, which I've drawn this really badly, as I tend to do, so it's more like this. This next column over, those are +2 in an ionic compound, except for boron over here. These are +3 in ionic compounds, and then I'm going to give myself a little more space on this side. The noble gases here don't form ionic compounds, and so they are not going to have a charge that we're going to think about. The halogens that start with fluorine here, they're always -1 in an ionic compound. The next column over, and really this gets interrupted by the stair-step line, but you'll get the idea. This next column over that has oxygen at the top is -2. Nitrogen and phosphorus in this next column over have -3 charge when they're in an ionic compound, all right? And so that's going to allow us to just pick something from like the +2 column, like magnesium, and something from the -3 column, like nitrogen, and say, all right, if we had magnesium nitride, that would be Mg2 plus N3 minus, as we just discussed, that would put a 3 here and 2 here, right? Mg3 and 2. So that's great for those. What do we do about the rest of the periodic table? Well, this is where it gets a little tricky. So again, periodic table. So everything that's part of the transition metals here, so this is the transition metals, and anything that's under the stair-step line in a metal, for reasons that we'll learn later on, these are called the p-block metals. And technically anything in that part below the periodic table that we're ignoring, that's called the f-block metals, but again, we're ignoring it. Anything in either of these two sections, these can have multiple charges. There are multiple possible charges in ionic compounds for these elements. And this presents a problem because before we didn't have to worry about it because sodium is always +1. Calcium is always +2. That's those don't change. The transition metals, depending on the compound, may be at a +2 charge, or maybe a +3, or maybe a +4, or maybe a +1. So we have to find some way to specify that, and the way we're going to do that is with Roman numerals. So what we mean by that is that let's say we have a compound iron, Roman numeral 3, oxide. This Roman numeral is going to give us the charge on the iron cation. So this is going to be Fe3+. Oxygen is from the part of the table we don't have to worry about because it's always 2-. So oxygen is 2-, and as we keep saying, that's a 2 and a 3. So that's Fe2O3. Now, I want to be really clear about this. The Roman numeral is the charge. It has nothing to do with what that subscript is. So notice that in iron 3 oxide, there are 2 irons. People get confused about this all the time. And so if this is one of the things you're confused about, I completely get it, but just be aware of it so that you don't get stuck in this trap, okay? So a couple of things that can happen here that are good to think about would be the compounds copper 1 oxide, which would be Cu +1, oxide, again, 2-. So we need 2 of those coppers to make this come out to be 0, right? So here, that would be copper 1 oxide. Again, the 1 is not the subscript. It is not the number of coppers. It is the 1 here in the Roman numeral is going to correspond to the charge on the copper. This gets a little tricky because a lot of times what we're given is the name of, or excuse me, the formula, and we have to generate the name, all right? So for example, let's say you were given the compound FeS. Now, iron being a transition metal, we're going to have to use a Roman numeral because we have to specify the charge. But how do we figure out the charge? We go to the periodic table and we look up sulfur, and sulfur has a 2- charge when it's in an ionic compound. If there's one of each, that means that again, the total charge has to be 0. So that means that the iron has to have a 2+ charge. So we're going to call this compound iron Roman numeral 2 sulfide. Whereas if you had this compound, all right, now we're going to say, all right, the sulfur is still 2- because sulfur doesn't change its charge. It's always 2- in an ionic compound. So what does the charge on the iron have to be? Well, that means that there's -2 charges. We'll just think about this at the particulate level. And for every one of those -2, there's 2 of the irons, right? So how do we make that come up to be a total charge of 0? Well, there's 6 negative charge. So each of these, if they're the same, has to be +3, right? So the iron here has a 3+ charge. So this compound is going to be iron Roman numeral 3 sulfide. All right. One more time. That number and that number are not related. What's related is the Roman numeral and the charge on the cation. All right. Those are the two that correspond to each other. Right? There's one other thing that happens in ionic compounds that we have to think about a lot, which is polyatomic ions. And there's a list of polyatomic ions that you just need to know. But just to give a couple of examples, NO3- is the nitrate ion. SO4 2- is the sulfate ion. OH- is the hydroxide ion. And NH4+ is the ammonium ion. Ammonium. All right. Now, what's weird about these is that the polyatomics are almost all, not quite all, but almost all, composed of nonmetals, which normally we would think of nonmetals only forming molecular compounds. It turns out that certain nonmetals can get together in groups and form stable ions if they're in an ionic compound, and those are known as polyatomic ions. All right. So if I were in charge, these would be called charged molecules or molecular ions. I am not in charge, so we are stuck with this. Okay. So, but how do we deal with these? Well, we deal with them just the same way we would any other ion. It just requires us to get around a couple of little mental hoops, okay? So for example, let's say you had the compound sodium sulfate, all right? Well, we know from the periodic table, sodium always has a charge of +1 in an ionic compound. Sulfate is SO4 with a 2- charge. Now, it may help you for a little while as you get used to these to put parentheses around this and realize that the whole SO4 group has a 2- charge, all right? So if you have a +1 and a -2, that means you need 2 of the +1s. So we would write this then as Na2SO4, all right? You don't have to look at this 4 to figure out anything about the ratio or the charges. This whole grouping has that 2- charge, all right? So what if you had something like aluminum sulfate? Well, aluminum, as we keep saying, has a 3+ charge in ionic compounds. The sulfate, again, I'm going to put parentheses around it to kind of keep us straight, has a 2- charge. So 2s and 3s, anytime we have this, we have to have 2 of the 3+ and 3 of the 2-. And so the parentheses here are really important to say that that whole SO4, there are 3 of them, all right? So we're always going to put parentheses around polyatomics when there's more than one. If it makes you comfortable, you can put them around the polyatomic even when there's just one. There's nothing super wrong with that. It's just we're not usually going to do it, or I'm not going to provide it to you that way. But if it helps you see it better, then that's a useful thing to do. It is required if there's a subscript associated with the polyatomic, like a 3 here, okay? All right, the best way to do this is to do lots of practice. So what I'm going to do is I'm going to give you a couple of practice questions here, and I want you to pause the video and after I've provided the practice here, and then try it, okay? So what I want you to do is write the formula for, let's do lithium oxide iron 2 nitrate and chromium 3 sulfate. And then I also want you to write the name of Fe2O3 CaSO4 and NH4 2s. All right, so go ahead and pause the video, and then I'll work out the answers. All right, I'm hoping that you have paused and worked these out on your own piece of paper. So we're going to do these. Lithium is in the first column, so it's always +1. Oxygen is in the 16th column, which is always 2-. So we need 2 lithiums to make this come out to be 0. Li2O is the formula. Iron 2 nitrate, that tells us that the iron is going to have a charge of 2. And then nitrate is one of our polyatomic ions, which has a -1 charge. So we need to have 2 of those. So that's going to be FeNO3, 2. Chromium, Roman numeral 3 sulfate. Well, the chromium is going to have a 3+ charge. Sulfate, as we just went over, is SO4, 2-. We have a 2 and 3 situation again. We're going to solve it like that, like we keep doing. So Cr2, SO4, 3. Right? Down here, iron is in the transition metals, so we have to use a Roman numeral for that. So oxygen has a -2 charge, so that's a total of -6 negative charge. So that means there has to be a total +6 positive charge. So that means each of the irons has to be 3+. So that's iron Roman numeral 3 oxide. One more time, that number and that number correspond. Right? Calcium is always just 2+, so we don't have to specify what its charge is. And then this is with sulfate. All right? So it's actually wrong to write the Roman numeral here because it's unnecessary, it's redundant, because it's always 2+. Calcium is. All right, this last one is ammonium polyatomic ion, and then just sulfide. It gets tricky to remember because we spend a lot of time doing polyatomics, but anytime you just have an anion that's from the periodic table, in other words, a monatomic ion all by itself, you just end it in the name of the compound inide. All right. I hope that's been some good review and practice for you all, and please feel free to leave me comments.